A single request leaves your service. A timer starts. You wait. Then the first word comes back. That wait feels like one thing. It is not. It is a stack of separate stages, and you control some of them and not others. By the end of this, you will look at a slow call and name the stage that is costing you. Start where you actually have control. Your own service. You build a request. It is just text in a structured envelope. It is the same shape of message your code already sends to any other web service. That interface is called an API. It is how one program asks another program to do something. There is no magic in the envelope. It carries your text, the name of the model you want, and a few settings. Your own code could build it with a plain HTTP client. The request goes out over an encrypted connection. Nothing reads it in transit. That encryption is not free. Opening a new connection costs a handshake. That is a short back and forth before any of your data moves. Do it on every call and you pay it every time. Reuse the connection and you pay it once. Then it crosses the internet to the provider's nearest entry point. This is where distance starts to matter. Light is fast, but it is not instant. A request from a machine 3,000 miles away pays for those miles twice, once going out and once coming back. Put your service in a region near the provider, and you delete part of that cost permanently. Choose badly, and you pay it on every call, forever. And then the request stops. It joins a queue. Here's the picture to hold for the rest of this video. Think of a restaurant kitchen. Your request is an order ticket. It goes onto a rail with every other ticket that arrived just before yours. You wrote the ticket. You chose what was on it. You do not decide how many tickets are already on the rail. That queue is the first stage in this journey that is not yours. Your ticket reaches the front of the rail. The first thing that happens is translation. The model does not read letters. It reads numbers. So your text gets cut into pieces. Each piece is looked up in a fixed vocabulary and replaced by an integer. Those pieces are called tokens. A token is a chunk of text, sometimes a whole word, sometimes part of one, sometimes just a space. The vocabulary is decided when the model is built. It does not change because of your prompt. Your text is simply matched against a list that already exists. Watch where the cuts fall. Common words survive intact. Rare words get broken into fragments. Punctuation often takes a slot of its own. The same sentence written two different ways can produce two different counts. That count matters for two reasons, and both of them are yours. The first is money. You are billed on how many tokens go in and how many come out. Every token in your system prompt is paid for on every single call. A long instruction block you wrote once is a charge you pay forever. The second is time. A longer prompt is more work to process before anything comes back. So this is the last stage you fully control, and it is decided before the request ever leaves your machine. Now, the integers become something stranger. Each token ID is used to look up a list of numbers, not one number. A long list, and every entry in it is a coordinate. That turns each token into a point in space. A space with far more directions than the three we can picture. You do not need to picture it. You only need one idea. Position carries meaning. The useful part is what the arrangement does. Tokens that get used in similar ways end up near each other. Nothing in there stores a definition. There is no dictionary anywhere in the model. There is only position. So when people say the model understands a word, what is actually true is narrower. The word has a location. That location is close to some things and far from others. Everything the model appears to know about that word comes from where it sits. This lookup is cheap. It is a table read, not a calculation. On the trace, it barely registers. Almost nothing you can do to your prompt makes this stage the problem. Now watch what your sentence really is underneath. The cloud flattens. The points become rows. The rows become a wall of decimal numbers scrolling past faster than you can read. That is what your text has become. A grid of floating point numbers. Every stage from here on is arithmetic on that grid. Here is the part most people get wrong. Your whole prompt does not get read one word at a time. It goes through the model in a single pass, all of it at once. Every token is processed alongside every other token. This is the one moment in the journey where the work is genuinely parallel. That is why these models run on hardware built for parallel arithmetic. This stage has a name: Prefill. Back to the kitchen. The chef does not read your ticket one word at a time. They take it in at a glance. The whole order lands together, and then they know what they are cooking. Prefill is the widest single block in the trace, and it grows with your prompt. Double the prompt, and this block grows in proportion. That is a lever you hold, and it is the biggest one in this whole video. It is also the reason a bloated system prompt hurts twice. You pay for those tokens, and you wait for them on every call. When prefill finishes, the model has everything it needs to produce one token. Not the answer, one token. The moment that first token is ready has a name too. Time to first token. It is the number your users actually feel. It is the gap between clicking and seeing anything at all. Everything before this point is setup. Everything after it is a grind. So what comes out of prefill is not a word. It is a score for every token in the vocabulary. Every single one. Tens of thousands of candidates, each with a number saying how well it fits next. Most of them are absurd. The model still scores them all. There is no shortlist step where bad options get skipped. Then one gets chosen. Not always the highest. Depending on your settings, the model samples from the top of that distribution. That is why the same prompt can come back differently on two separate calls. That chosen token is converted back into text and pushed out to you immediately. It does not wait for the rest of the answer. If you are streaming, it goes on the wire the moment it exists. This is the kitchen sending out the first dish while the second is still in the pan. The table starts eating. Nobody waits for the full order to be plated. Streaming does not make the total any shorter. The last token still arrives when it was always going to arrive. What changes is the weight the user is aware of. And that changes what you should measure. If you only time the complete response, you are measuring the last dish. Your user reacted to the first one. Two systems with identical total latency can feel completely different. One showed a word in half a second. The other showed nothing until the end. Now the model does the whole thing again. To produce token 2, it runs another pass. Token 3 needs another. Every token you receive is its own trip through the model. And these cannot overlap. Token 5 cannot be computed before token 4 exists, because token 4 is part of the input that produces it. This is where the kitchen analogy breaks, and it is worth saying plainly. A kitchen can put two cooks on two dishes and finish them at the same time. Decoding cannot. There is a strict order. No amount of extra hardware removes it. That is the single most important asymmetry in this whole video. Prefill gets faster with better hardware. Decode mostly does not. So prefill was wide and parallel. Decode is a long line of thin, identical slices, one per token, which gives you the shape of the whole thing. Your total weight is the time to the first token. Then add the number of tokens you asked for, multiplied by the time each one takes. Read that again as a lever. The length of the output sits inside that formula. Asking for a summary in 3 sentences instead of letting it ramble is not a style preference. It is a latency decision. It is also a cost decision because you are billed per token on the way out as well. And notice what is missing from that formula. The size of your prompt is not in it. Prompt length drives prefill. Output length drives decode. 2 different levers, 2 different stages, and people confuse them constantly. So color the trace in 2 groups. Yours, the size of the prompt, how far your service sits from the provider region, whether you reuse connections, how many tokens you asked for, whether you stream, theirs, how deep the queue was when you arrived, how much other traffic was sharing the same hardware, how the provider decided to batch you with other requests. Look at the split. A meaningful part of your wait was decided by conditions you cannot see and did not cause. That is not a reason to give up on it. It is a reason to stop tuning the wrong half. Here are the two cases you will actually meet. If your calls are slow and your prompt is enormous, that is yours. Cut the prompt. If your calls are slow and your prompt is small, look at when it happens. If the slowness shifts at different times of day, that is a cue. No prompt rewrite will touch it. Your options there are retrees, a different region, or a different capacity arrangement. Measure the stages separately. A single total latency number cannot tell those two situations apart. It averages a thing you control together with a thing you do not, and then hides both. Record time to first token and total time as two different numbers. Record your input and output token counts next to them. That is enough to diagnose almost every slow call you will ever see. One request, end to end, one more time. Out of your service, over the encrypted connection, across the distance, into the queue, text into tokens, tokens into numbers, the whole prompt through the model in one pass. That is prefill, and that is your first token. Then one pass per token, in strict order, until it stops. 6 stages, not one wait. Next time a call is slow, do not ask why the model is slow. Ask which stage grew.